Now, in this lecture video, we start looking at methods for making inferences about two population means. Specifically, we'll look at hypothesis test and confidence intervals for two population means, and we're going to be looking at the following situations. The first major category of procedures that we're going to look at are applicable when we have independent samples. So we're going to have one sample from each of two populations, and those two samples are independent of each other. Within this category, we'll look at several situations. The first situation is when we know the population variances. The second broad category of situations is when we don't know the population variances, and within that category, we'll look at two subcategories when it's reasonable to assume that the population variances are equal, and also the situation when it's not reasonable to assume that the variances are equal. And then finally, we'll look at the situation where the samples are not independent, but they are dependent, specifically when we have what are called paired samples. So the hypotheses that we have available to test are the same three types of hypotheses that we've seen in the past. We have a two-tailed test, a left-tailed test, and a right-tailed test. Now, the two-tailed test has a null hypothesis, which says that the difference in the population means mu1 minus mu2 is equal to some hypothesized difference, which I'm denoting by a lowercase delta sub 0, against the alternative hypothesis, which being the logical complement of the null, is therefore that the difference between the population means is not equal to that hypothesized difference. The left-tailed test has a null hypothesis that says that the difference between the population means mu1 minus mu2 is greater than or equal to, it's at least delta 0, this hypothesized difference, against the alternative hypothesis that the difference is less than delta 0. And then finally, the right-tailed test has a null hypothesis that says that the difference between the population means mu1 minus mu2 is less than or equal to the hypothesized difference, delta 0, against the alternative hypothesis, which says that the difference between the population means is greater than delta 0. Now, these hypotheses are stated very generally, allowing for any value delta 0 that is pertinent or applicable or relevant in a given situation. But in many situations, the value of delta 0 that is used will be 0. And so when that happens, we can state these hypotheses in a couple different ways that may, in some cases make more intuitive sense, but they can always still be stated in terms of differences between the population means. Now, let me just say that while in many cases the appropriate value for the hypothesized difference, delta 0, will be 0. And again, in many cases that will be the case, but in many cases it won't be. Let me just say that there are criticisms out there in some of the literature criticizing this kind of hypothesis testing where a value of 0 is used. And they say that in most scientific research that a value of 0 is really not relevant. It's really not the appropriate value to use. And in some of those statements in the literature, and let me just say that some of these comments are coming not only from outside statistical literature, but even within statistical literature itself, especially from folks who are arguing from a Bayesian standpoint. So, people will criticize the use of a hypothesized value of 0, and in many cases, they will act as though that is the only value that is ever used or can ever be used. But that's certainly not the case, all right? Like I said, we can use a non-zero value of the hypothesized difference if it makes sense in a given situation. And so let me just, I just wanted to warn you of that and to recommend if you are going to test a hypothesis, if you are in engineering or some scientific field, and you have you have to compare the means of two populations, that you think very, very carefully. Don't just use a value of 0 automatically, at least. Think very carefully about the appropriate value of delta 0 that you use. And let me just say that, as an example, in the context of medical studies, health studies, clinical trials, or something like that, that the value, let's suppose that mu1, that mu1 and mu2 are such that we want to, we want mu1 to be less than mu2, and maybe we're developing some kind of a pharmaceutical drug, and we're wanting to reduce blood pressure. All right, and so mu1 might be the blood pressure. Actually, it would be the opposite. So let's say that mu1 is the blood pressure before taking the drug, and let's let mu2 be the blood pressure, and in particular, let's say the systolic blood pressure after taking the drug. Well, and so we want to reduce the blood pressure, and so that's going to be accomplished if we can conclude that mu1 minus mu2 is greater than 0. But I would argue that the hypothesized value of 0 may not be the appropriate value to use, because what if the difference is only 0.01? Well, that's not a very big change, is it? And so we might want to insist that the drop be at least 5 points, or greater than 5 points. Let's put it that way. We might say that we want the drop or the decrease in the systolic blood pressure to be more than 5 points. And so in that case, the appropriate value of D0 to use would be 5, not 0. So in general, in those kinds of studies, you would want to choose as a value of delta 0 the minimum clinically relevant value that you want to accomplish, or that is needed for that application. If you're not doing health studies, maybe you're engineering or maybe some other scientific field, then you would want to choose the minimum scientifically relevant value. And that minimum scientifically relevant value is not necessarily 0. In fact, in many cases, it's going to be something greater than 0. So you just need to keep that in mind as you set these up. But for those situations where a value of 0 for the hypothesized difference is appropriate, then the hypotheses can be stated in terms of differences, as we've got here in the first of each of these 3 bullet points. But we can also state it in perhaps a more natural way. For example, for the two-sided test, the null hypothesis would be that mu1 is equal to mu2 against the alternative that mu1 is not equal to mu2. So we can restate the hypotheses in that way, and sometimes that may be easier for the readers of a study to interpret. So let's talk about the assumptions and the sampling framework for the situation where we're dealing with independent samples. And so we're going to have 2 samples, one sample from each of our 2 populations. We need to denote the observations within each of these samples. And so in this section, we're going to be using the letter Y to represent the response variable for both of our samples. But because we have 2 samples, we're going to use double subscripting to identify which sample and which observation within a given sample that we are talking about. So the convention here is that we're going to allow we're going to use the first subscript to identify the sample number, and the second subscript to identify the observation within the sample. And so Y11 is the first observation within the first sample. Y12 is the second observation within sample 1, and so forth. And so we have a random sample of size N1 from a population with mean which we'll denote by mu1 and a variance which we'll denote by sigma 1 squared. Similarly, y21 is the first observation in sample 2, y22 is the second observation in sample 2, and so forth, out to y2 sub n2, or I'm sorry, y2 n sub 2, which is the last observation in the second sample. This is a random sample of size n2 from a population with mean which we will denote by mu sub 2 and a variance which we'll denote by sigma 2 squared. So we have one sample from each of our two populations. Notice that the sample sizes, it may not be obvious from what we're doing, but because we're subscripting the sample size with the sample number, that's just a reminder that the sample sizes do not need to be the same. If they needed to be the same, then we would not subscript them with the sample number. And then finally, not only are the observations within a sample independent, but the two samples are independent themselves. So sample 1 and sample 2 are independent of each other. And so we will let y bar 1 be the mean of sample 1, y bar 2 be the mean of sample 2. All right, and that we know that if we're sampling from a normal distribution, we know then that y bar 1 is exactly normally distributed. And y2 would be exactly normally distributed as well. If populations 1 and 2 are both normally distributed, then both y bar 1 and y bar 2 would be exactly normally distributed. Now, if the populations that we're sampling from are not normally distributed, then for sufficiently large samples, by virtue of the central limit theorem, we then know that the sample means will be approximately normally distributed. And so that's why I've got that in parentheses. Now, in reality, the more likely scenario is that the population that we're sampling from is not exactly normally distributed. And so we will need to make sure that we have a sufficiently large sample to be able to appeal to the central limit theorem and for the normal distribution to be a good approximation to the sampling distribution of y bar 1 and y bar 2. Now, regardless of any of that, we know that the mean of the sampling distribution of y bar 1 is equal to mu 1, the mean of population 1, and the variance of the sampling distribution of y bar 1 is equal to sigma 1 squared over n1. Okay, so those two facts are true regardless of whether the population that we're sampling from is normally distributed. Similarly, the mean of the sampling distribution of y bar 2 is mu 2, the mean of population 2, and the variance of y bar 2 is equal to sigma 2 squared over n2, where sigma 2 squared, again, is the variance of population 2. Now, because the samples are independent, stochastically independent, y bar 1 and y bar 2 are stochastically independent as well. All right? Now, let me also just point out here that y bar 1 minus y bar 2, so if the two populations are exactly normally distributed, then y bar 1 minus y bar 2 will be exactly normally distributed. However, if the populations are not exactly normally distributed, then as long as the samples are both sufficiently large, then y bar 1 minus y bar 2 will be approximately normally distributed. Now, having said that, regardless of whether the regardless of whether the populations are normally distributed or not, we know that for any sample size, the difference between the sample means, y bar 1 minus y bar 2, the mean of the sampling distribution of that random variable is equal to mu 1 minus mu 2, the difference between the population means. And because the samples are independent of each other, the variance of y bar 1 minus y bar 2 is equal to that quantity right there, sigma 1 squared over n1 plus sigma 2 squared over n2, the sum of the variances of y bar 1 and y bar 2. And so because of that, because that's the variance of the sampling distribution of y bar 1 minus y bar 2, we know then that the standard error of y bar 1 minus y bar 2, also known as, or we know that that's the standard deviation of the sampling distribution of y bar 1 minus y bar 2 would be equal to the square root of that quantity, which I've got listed here. And so based on that information, all right, and notice, what we're doing here, we are coming up with, we're thinking about and determining the sampling distribution of the difference in the sample means. And so because of what we've just determined, this implies that this random variable, y bar 1 minus y bar 2, minus the hypothesized difference delta 0 over the quantity which is the standard error of y bar 1 minus y bar 2, for sufficiently large samples that that will be at least approximately normally distributed. The mean of the sampling distribution of this new random variable will be mu1 minus mu2 minus delta 0, and the standard deviation of that random variable will be 1. Now, if the null hypothesis is true, in other words, if mu1 minus mu2 is equal to delta 0, then what this means then is that this random variable will have a standard normal distribution. Now, if the population variances are known, if sigma 1 squared and sigma 2 squared are both known, then once the samples have been obtained, this random variable that we've got up here can be computed and used as a test statistic or as a basis for constructing a confidence interval. Now, if the population variances are not known, which is really the more realistic scenario, then they will have to be estimated from a sample or from the samples, and a modified version of this random variable will have to be used in which sigma 1 squared and sigma 2 squared are replaced by their estimates. And so that's similar to what we did back in the previous module when we were testing hypotheses about a single population mean. And if we didn't know the population variance, sigma squared, we had to estimate it. And you'll remember that we estimated it with the sample variance. You'll also remember that when we did that, the resulting random variable didn't have a standard normal distribution, but it had student's t-distribution. And so that's going to be a similar kind of thing that happens in this module as well. When we replace sigma 1 squared and sigma 2 squared with their sample-based estimates in this formula here, then the resulting random variable no longer has a normal distribution. It will have some t-distribution, which we'll talk about later. So the test statistic, z-calc, is given by this expression, the difference between the sample means, y bar 1 minus y bar 2, minus whatever the hypothesized difference is, delta 0, divided by the true standard error of y bar 1 minus y bar 2, which is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. The sampling distribution of the test statistic z-calc will be the standard normal distribution, or at least approximately the standard normal distribution, if the null hypothesis happens to be true. And so that is the reference distribution from which we will get the critical points for setting up the test. And so for our two-tailed test, we would, and performing it at a significance level of alpha, we would reject the null hypothesis. If z-calc is either really small, in other words, if it's less than negative z sub alpha over 2, or if it's really big, specifically if it's greater than positive z sub alpha over 2. For the left-tailed test, we would reject the null hypothesis if our test statistic z-calc is small, less than negative z sub alpha. And for our right-tailed test, we will reject the null hypothesis if our test statistic z-calc is greater than positive z sub alpha. Now, the p-values for these three tests have the same type of formulas that we've seen any other time we've used any kind of a z-test. In other words, a test where we go to the standard normal table to get our critical points. And so for the two-tailed test, the p-value of the test will be 2 times the probability that the standard normal random variable z is, and this needs to be greater than or equal to, Great. So these inequalities need to be non-strict. And so I'm going to make those changes in your notes, and I'm going to fix those in my notes as well. Okay, so I've got those fixed. So the p-value for the two-tailed test is 2 times the probability that the standard normal random variable is greater than or equal to the absolute value of the observed value of the test statistic z-calc. For the left-tailed test, the probability, or the p-value, is the probability that a standard normal random variable is less than or equal to the observed value of the test statistic z-calc. And for a right-tailed test, the p-value is the probability that a standard normal random variable is greater than or equal to the observed value of z-calc. Now let's also talk about constructing confidence limits, lower confidence limits, upper confidence limits, and confidence limits for a two-sided confidence interval. So because this random variable here, which is the standardized version, the true standardized version of the difference in sample means, this has a standard normal distribution, or at least approximately so. It follows that the approximate probability that this standardized version of the difference in sample means is less than or equal to z sub alpha is 1 minus alpha, or at least approximately so. And we can, as we've done in the past in other sections and so forth, we can rewrite the event inside the parentheses here to get an event where mu1 minus mu2 is on one side of the inequality all by itself. And so this shows that the probability of getting a hold of two samples for which this quantity here is less than or equal to the difference in population means is 1 minus alpha. And so this means that in repeated sampling, the random variable y bar 1 minus y bar 2 minus z sub alpha times the true standard error of y bar 1 minus y bar 2 will be less than or equal to the difference in population means mu1 minus mu2, approximately 1 minus alpha times 100% of the time. Equivalently, the difference in the population means mu1 minus mu2 will be greater than or equal to this random variable, approximately 1 minus alpha times 100% of the time. And so because of that, we call this random variable y bar 1 minus y bar 2 minus z sub alpha times the true standard error of y bar 1 minus y bar 2. We call this random variable a 1 minus alpha times 100% lower confidence limit for mu1 minus mu2. Now, once we've gotten a hold of our data, once we've gotten a hold of the two samples and constructed that point, then we say that we are 1 minus alpha times 100% confident that mu1 minus mu2 is greater than or equal to this lower confidence limit. Similarly, we can come up with a probability statement for the event that this standardized version of the difference in sample means is greater than or equal to negative z sub alpha, and that probability is 1 minus alpha. We can then rearrange the event inside the parentheses to get mu1 minus mu2 on one side of the inequality by itself. And so we get this probability that mu1 minus mu2 being less than or equal to this random variable, where instead of subtracting this quantity from the difference in the sample means, we're adding it. You see that right there. And so that probability, because these events are equivalent, they have the same probability of 1 minus alpha. And so this implies that in repeated sampling, the random variable given by the difference in the sample means plus z sub alpha times the true standard error of the difference in sample means will be greater than or equal to the difference in the population means mu1 minus mu2, approximately 1 minus alpha times 100% of the time. An equivalent way to say that will be that the difference in the population means mu1 minus mu2 will be less than or equal to that random variable, approximately 1 minus alpha times 100% of the time. And so because of that, we call this random variable a 1 minus alpha times 100% upper confidence limit for the difference in population means mu1 minus mu2. Now, once we have our samples, once we have our data, we calculate this endpoint or this quantity, this random variable, this upper confidence limit. And so the way that we interpret this is by saying that we are 1 minus alpha times 100% confident that mu1 minus mu2 is less than or equal to this upper confidence limit. Now, if we construct both a 1 minus alpha over 2 times 100% lower confidence limit, as well as a 1 minus alpha over 2 times 100% upper confidence limit, and then we put those two confidence limits together and form an interval, then what we have is a 1 minus alpha times 100% two-sided confidence interval estimate of the difference in population means mu1 minus mu2. And so once we have that, once we have our data, once we've calculated the two endpoints, and so therefore we have our confidence interval, we say that we are 1 minus alpha times 100% confident that the difference in the population means mu1 minus mu2 is somewhere in this interval. So let's look at an example. This example involves production fabrication systems. So a production plant has two fabricating systems. One uses automated equipment, the other is a manual operation. Since the automated system costs more to install, management wants to know whether it provides increased production in terms of the mean number of finished products fabricated per day. Experience has shown that the daily production of the automated system has a standard deviation of 10 units, whereas the standard deviation of the manual system is 20 units. Independent random samples of 100 days of production are obtained from company records for each system. The sample for the automated system has a mean daily production of y bar 1 equal to 254 units, while the sample from the manual system has a mean of y bar 2 equal to 248 units. The question is there sufficient evidence to conclude that the automated system is superior to the manual system? That is there sufficient evidence to conclude that the automated system has a higher mean daily output than the manual system? And so let mu1 denote the average number of units fabricated per day by the automated system, and mu2 the average number of units fabricated per day by the manual system. Now, in this situation, because we've not been given a specific value above which the automated system is to have produced more than the manual system, we're going to use a hypothesized difference, a delta 0 of 0. But this is a great example of a situation where we actually may want to use a non-zero value of the hypothesized difference, for example, to take into account the increased cost of installing the automated system. But for now, we're going to go with this hypothesized difference of 0. So the hypotheses to be tested are given below. The null hypothesis being that mu1 minus mu2 is less than or equal to 0. In other words, that mu1 is less than mu2, against the alternative hypothesis that mu1 minus mu2 is greater than 0. In other words, that mu1 is greater than mu2. Okay, so this is a right-tailed test, and we're performing this test at the 0.05 level of significance. And so the rejection rule will be to reject the null hypothesis if our test statistic z-calc is greater than the upper fifth percentage point of the standard normal distribution, which we know is 1.645. So then we use our sample data, the sample summary statistics that we've been given, the two sample means, along with the population standard deviations, and we calculate the value of the test statistic, which we find to be 2.6833. Since 2.6833 is greater than the critical point, 1.645, there is sufficient evidence to reject the null hypothesis. And so therefore we conclude that mu1 minus mu2 is greater than 0. And I see I need to fix a typo here. Let me go do that. So we conclude there is sufficient evidence at the 0.05 level of significance to conclude that the automated system produces more units per day on average than the manual system. Okay, now let's look at the p-value method for performing this test. The previous method we used the critical point and test statistic method. We can also use the p-value method. So that requires us to calculate the p-value for the test and then compare that to the significance level we're using for the test. So the p-value for this test, because it's a right-tailed test, is equal to the probability that a standard normal random variable is greater than or equal to 2.6833. That probability is approximately 0.0037. So we would need to, what I would do is just round this z-value to 2 decimal places because that's the precision for the z-values that we have in the standard normal table. And then we would get this approximate probability. Now, since 0.0037 is less than or equal to 0.05, we reject the null hypothesis at the 0.05 level of significance and therefore conclude that mu1 minus mu2 is greater than 0. Now, we're not done really because the natural follow-up question would be, okay, how much bigger? If we're concluding here that mu1 is bigger than mu2, the question is, how much bigger is mu1 than mu2? And so what we want to do is construct the appropriate type of confidence interval at the appropriate confidence level. And what we mean by that is we want the confidence interval to be consistent with the hypothesis test that we just performed, and we want the confidence level to be consistent with the significance level that we used for that test. Because we want the type of, we want the inferences that we draw, the qualitative inferences, to be the same as the inference that we draw from the hypothesis test at the appropriate confidence level. So the formula for the, well, first of all, we're going to perform or construct a lower confidence limit because the corresponding test was a right-tailed test, so the corresponding kind of confidence interval would have a lower confidence limit, and the appropriate level, confidence level for this lower confidence limit is 1 minus alpha times 100%, 1 minus 0.05, so 0.95 times 100%, or 90%. And so we see here that using the formula given in the notes and performing the calculations, we get a 95% lower confidence limit of 2.32. And so we can say that we are 95% confident that the difference in population means, mu1 minus mu2, is greater than or equal to 2.32. Equivalently, we can say that we are 95% confident that mu1 is at least 2.32 units larger than mu2. So the we conclude here that we're 95% confident that the automated system produces at least 2.32 units more per day on average than does the manual system. So that is that shows how to use this procedure for comparing two population means via their difference when we know the population standard deviations. The more realistic situations when we don't know the population standard deviations. That's the much more common scenario, and so we're going to look at that in the next lecture video.